Okay, so I think there's lots of different ways to do this kind of a bash tutorial. This is the way somebody did it for a course I went to, which I think worked quite nicely just because it let people ask questions before they were let loose on their data. So I'm going to try and go through this bash refresher, which I've put together and will be available. I'll send it around in a minute, or maybe one of the other organizers can put it in the chat now. But otherwise, you can just sit back and watch for now and then go through it at your own pace. So the first part of this is really about general bash commands, and bash is this kind of language that your Unix shell or Unix-based shell, or if you're using a Windows machine, whatever your kind of conversion tool will be interpreting. It's how you communicate with your computer. And one of the first things you'll notice if you open terminal or this command thing for Windows is you'll be given this prompt here. So the prompt will normally tell you the machine that you're on, and it will tell you your user information or something like that. And you'll see this blinking cursor, probably, which is just telling you that it's waiting for a command. What we're going to do first is actually log into the cluster. So when you do this, you could do this all on your local machine if you don't have cluster access or on the cluster. And to do that, we're going to use SSH, which is producing a secure connection to the cluster. You'll then type in your username and then the address of the cluster. And you'll then be prompted for this password. So as you saw in some of you might have seen in the Slack channel, this will not actually show your password. So don't expect it to. But when you type it in and you click enter successfully, you should be prompted with this kind of welcome message onto the cluster. So the first thing you probably want to do when you get into a position like this is to say, well, where in this computer system am I? You can see here that my prompt has changed. So it's saying that I have this. This is actually to do with the conda environment, I think. And it's saying what my username is on this cluster. And it's telling me here that I'm on a login node. So this will become useful later on to understand what you should and shouldn't do depending on where you are in the cluster. You do not want to be running very, very high requirement jobs on a login node. They are really designed to kind of navigate your way through the cluster system. So you can actually check where you are using this pwd command, which I have here. And so if you do pwd and type enter, this will give you the full file path. So here you see I'm in cluster, the home directory, and then my directory. So I am actually going to make a new directory. Now you'll see how bad I am at typing. It's going to be great. Okay, so now you can see actually that I made a directory. Here in the example, it's oh no. Here I made bash refresher. And then I use the command mkdir, so that's make directory. And I use cd to change directory into this new directory. Many of you who are less confident with bash, maybe, I mean, I definitely know this is true of me, is like understanding where you are and where you are in relation to the files you want to use and interact with is one of the hardest, or it's a steep learning curve, and it's one thing which you will eventually get very good at, I think, but it can be a bit daunting. So play around with some of these settings and these commands as to how you change your location. You can also do things like you can use relative expressions. So for example, here in this tutorial on the right, this ... this is telling the computer that you want to move to the previous directory. So if you think of directories as this hierarchical structure, if you do cd and then ... you'll see now I'm not in bash refresher anymore. I've moved back up to my home directory. So I can move back in. And you can also give full file paths. So actually, instead of just using relative file paths, which can be a bit hard to understand if you have a lot of scripts written out or something like that, you can always give it a full file path. And your full file path will also always start with the slash. So the slash means that you're starting basically from the root of the file structure. And in this case, it will be cluster home, my name, and then bash refresher. So whenever you're using file paths in scripts, you can always use this option or this option. Then, obviously, the thing we often want to do is make, move, and change files. So for this example, we're just going to make a file. You can make an empty file using touch. So if we do touch file1, we have now made a file, but we can't see it. So you can use the list command, ls, to see what is in your current directory. So pwd tells us where we are, and ls will tell us what's in our directory. You can also do ls and give it the full file path, which would return the same file. When you're dealing with very big files, actually, I'll just move this up. When you're dealing with very big files, you might want to check the size of the files that they're in the directory you're working with. And for that, you can do ls-lh. This is saying list, and then tell me what's in, the content of each file and the permissions. And the h means in a human readable format. So if we just do ls-l, you'll see that, this is a bad example, but if this was in, this number here will always be in bytes. So in this case, we have an empty file, so it's saying that the file has 0 bytes. If you have like a whole thing of sequencing data, this will be like millions and millions and millions. But if you do -h, it will tell you how much it is in gigabytes or megabytes. So we can also move this file. So if we want to move file 1 to the previous directory, we don't want it in bash refresher anymore, we can use mv for move. We can do file 1, and again here we could use this relative file path. So this is saying move file 1 up 1 step in our hierarchy. Then if we do ls, you'll see it's no longer here. And actually, if we move back a directory, I have some other files in here, but you'll see file 1 is right here. Okay. So yeah, we can also move files to the current directory using this full stop. So you can do something like move, and then I can do, let's see, what can I move here? I'll just move this script, so my script, and I want it here now. So the dot means here, and then if I run ls, you'll see my script is here. Okay. We're going to need file 1 for later, so I'll just make it again. One of the things which I like to use if I need to write small scripts or anything in bash or on the cluster, and I can't be bothered to move a file between the cluster and my local machine, is I will use vim. I'm pretty sure all of the instructors will have their favorite text editor. There are many others you can use, things like Nano. I like vim, but it has a very kind of steep learning curve. But for this introduction, you'll just be using very basic things. So to use vim, we can do vim and type the name of the file we want to create, in this case, test file. Then everything will change. You are now in vim. And if you've tried to use vim, you might know that getting into vim is not the problem, but actually leaving vim is often the problem. But we're in vim. If we want to type something, so if you were to type now, nothing will come up. If you click the I button on your keyboard, you'll see at the bottom here now this says insert. And here we can now type. So things will show up. We could type like this is our file. And now we want to exit vim again. So what we want to do, as I've put here, is we want to use the escape button. So escape will take you out of insert mode. So now if you press buttons on the keyboard, you're not just typing. And we want to tell vim that we want to write this file and we want to quit. So the W here means write, the Q means quit. So if we type colon, you'll see it starts to pop up down here. WQ, and click enter. We are now out of vim. And you'll see that if we do LSLH, that test file, which we just made, has some stuff in it. You can actually check what's in that file using something like less. So you can do less test file. And if we click enter, it will bring us out in less. So you can see this. If you want to exit less, you just press the Q button on your keyboard. You can do things like cat, which will just paste it all to standard out, which will be here. And yeah, I think that's the main thing. So we'll be using vim to make some scripts later on. If you have a favorite text editor that you prefer using, just go ahead and use that. It's not a problem. They all do the same things. I'm a fan of loops in bash. I think they can be very useful, especially if you're doing repetitive jobs on things. Loops are a bit different. If you're used to using something like R or Python, they all have their different quirks of how loops work. In bash, you can see this example syntax here. The example that we're going to do here is we're going to make some other files to join file 1 in our directory. I'm actually just going to remove the other 2 files. So you can use rm for remove. So in this case, I'm going to remove my script, and I'm going to remove the test file. Okay. So you can see now I just have file 1. And what this loop is going to do is it's going to say for I in 2 to 5. So this will go 2, 3, 4, 5. Do, and this is telling bash, this is what I want you to do. It will then echo, so it will paste or return the I that we're using, the value of I, in this case, the number. It will then make a file called file, and then the number, in this case, again, I, and then it will finish. Here, I could be other things. There are times when you might want to use file names here. There are times when you might want to use things like prefixes if you want to change files of different types. Here we will just use the number. So every time you see dollar, curly brackets, I, close curly brackets, this will paste 2, 3, 4, and then 5 for each round of the loop. So you can copy this and you can paste this, click enter, and you'll see because of this echo command, it's telling me which round it's on. So we're saying I'm doing 2, I'm doing 3, I'm doing 4, I'm doing 5. Now when we do ls, you'll see there are now 5 files in the directory, each with file and the number of the loop. Okay. We can also use loops to do other things like move files or add contents to files, which can be really useful if you want to append files in a loop. What we'll do here is we're actually going to rename these files. Instead of just being ambiguous files, we're going to add this prefix, oh no, to the file for this workshop, not because you're freaking out. And then we're going to add some very short fake sequencing data to each of these files. So that's what's happening here. So you're going to echo. This is a faster file example. You're going to have your header, and then you're going to have your sequence. So this is obviously, there's no quality scores here, moving on from the thing we just did. And then we'll have a second sequence with faster heading 2. So if I first do lslh, you'll see here that all of these files are empty. So after running this, we would hope they are not empty. They should have stuff in. So we run the loop. You'll see it's told me this time $file is the variable name that we're using, and it's returning the file name each time. If we do lslh, they all have the same content, the same number of bytes, and we can look inside one of them just like this, and you'll see here now we have 2 faster reads. So you might want to put the .faster on the end of this file, for example, but it doesn't really matter right now. One thing, if you're less familiar with bash, is to use the tab key. The tab key is your best friend. So in this example here, if I just type less and then O, and I click tab, it will return this. Your computer should make like a weird noise probably. And it's basically saying it will auto-complete here. And then if you double click the tab, it will tell you all of the options you can select from. So this is really useful and will probably be useful later on when you're trying to find like Conda environments and things like that, because you can actually search through directories this way. If you know, okay, the software I'm looking for starts with a P, you can just use P. You can start typing P and then use tab, and you can see all the folders and stuff that begins with a P. So in this case, we want to look in here. And when I showed you cat earlier, the other thing cat is useful for is to concatenate files. So if you were to post kind of 2 files here, what it will do is it will actually merge the 2 of them. So here, this larger than sign is basically saying, pipe the output of these 2 files into this new file. So we're going to run that too. Okay, so now we should have a 6th file, and that's here. And you can see using lslh that this has more content than the other, so it should have double the content. Now we'll move on to sed. Sed, I think, is a very powerful, I don't know if you'd call sed a language, but a powerful tool that you can use. And what sed allows you to do is to kind of find and replace is one thing sed can do. I'm going to show you here 3 different kind of languages or tools or programs. Each of them is very, very powerful, I would say, and you will probably use them a lot. But I've just included some examples of what they can be used for. So one of the things I use sed for more often than not is to find and replace. And the syntax of sed is basically you call sed, the program, and then it has this funny syntax where it has s/something/something/g. And this combination of S and G is basically your find and replace. There are other things you can use here. I'll let you explore those on your own. You can find, I've put a link here to some more sed tips and tricks. In this case, what we're going to do is we're actually going to append one of the faster headers. So if you remember from above, each of the faster headers just has larger than, which is how all faster headers look, faster header, and a number. This time what we want to do is we want to make sure that we understand that the FASTA headers in file 2 say genome 2. So for example, if we want to treat this as a different individual or a different species or something like that, we might want to add that to this larger than symbol. So what we're going to do is we're going to actually pipe the output of that to a new file called oh no file 2 new headers. Okay. So here, if we do oh no file 2, this is the old file, you'll see that they still have FASTA header 1, FASTA header 2. And if we run this on our new file, you'll see that it's now appended this genome 2 bit to the header. So that's really, really useful. Another thing you can do if you're feeling risky is to use sed-i, and sed-i will actually just append the file that you're currently working on. You don't need to pipe it to an output. You're basically saying, find and replace in this file, and I want to keep the same file. So in this case, what we're going to do is we're going to find and replace for genome 3 in file 3, just using sed-i. So here I haven't piped to any file, but if we do cat and then our new file, we'll see that it has this appended header. Are there any questions on anything we've covered until now? Just quirks or anything? No, excellent. Okay. Maybe it's a bit basic, but with such a diverse audience, I thought it's best to start from the beginning. And if people have questions, feel free to just shout them out. So one of the other useful things that I use daily, many times a day, is grep. Grep will basically help you extract information from a file. You can give grep any kind of character sequence. You can use wildcard things in here too, which we can talk about later if you're interested. But grep will basically search for any instance in our file of this character. And here we specify the file name. So in this case, we're hoping it should return our FASTA headings because they are the only lines that have this larger than symbol. So if we run it, we'll see here, it will return these. So if you've ever worked with a genome assembly, for example, you've probably wanted to see, how many FASTA headers do I have, or how many chromosomes or contigs or scaffolds is this genome in? And you'll probably use a command like this. You can read out all of the FASTA headers. And the other thing you can do is you can combine grep output with the word count-l, which will tell you how many lines there are. So if we were to just do word count-l on this file, it will count all of the lines. It will return 4 because we have a header sequence. If we grep for the larger than symbol and then pipe it to word count-l, this will actually return. Oh yeah, sorry. So this is our combined file that we made earlier. So actually, if we do it for file 1 that we were just looking at, it should return 2, these two. And if we run it on file 6, this is the one that we combined a bit of a while ago. We now have 4. So you can see there are 2 sequences in file 1 and 4 in file 6. Now, one of the other things we might want to do with grep is we want to say, well, I know that this header exists, or I know that there are headers here, but I actually don't want this line, just this line. I want this line and the line following it. So in sequence data, you often have this kind of interleaved file format where you have some kind of identifying line followed by a line of interest. And here we can use this flag, this -a, and this is basically saying after. So this number that we specify here is saying how many lines after the line that grep finds do we want to return. So in this case, it should return this header line that it finds because we're searching for FASTA header, and then it should return the following line. So if we just run this on its own, it will look like this. So you see here now we have the FASTA header and the first sequence. And grep also has this cool command, this grep-v, which is basically saying remove any lines, or don't show me any lines that have this this larger than symbol in this case. And so this can be useful to extract all sequence lines, for example, in our file, because we can say, give us all of you could just grep for a nucleotide, but obviously your FASTA headings will pop up because they have A's, T's, and G's in. So here you can say, search the sequence that follows every FASTA header, and then don't show me the header line, essentially. So if we run this, you'll see that it just returns the sequence in this case. Okay, there's another cheat sheet here for grep, and I think it will be good if you look through that whenever you get stuck There's lots of really cool things you can do with all of these. And actually, to some extent, some of these different examples will do different things. So you can do a lot with sed, you can do a lot with grep. The next example I'm going to show you is with awk. I don't know if awk is actually short for awkward, but the syntax can be very awkward. So it's something to bear in mind when you're using awk. But like everything in bioinformatics, you are not the first person to have the problem you're having, and good Googling will normally help you sort it out. And if you look on Stack Overflow for things like how do I extract this, or how do I make this column this, there will often be multiple suggestions, and pretty much one of them will always be awk. There are some really hardcore awk users. What we're going to do for this example is we're actually going to make a text file. So here we have some whitefish data from the study system that I used to work on. And what this data is going to have, we're just going to make it by piping all of this information into a new file. So you can actually, this also can be useful for submitting jobs, where you can give all of your commands here and pipe it into a submission script. But here, if we run all of this text, and click enter, we can look at this. You should see this sample info.txt file, which should be a lot bigger than the others. And if we look in it, we will be able to see all our data. So in this case, what we have is our individual number, the species of the sample, the lake that it comes from, head length, and body length. I can't spell length. That's great. So this is, we often work with data with different file formats, different delimiters in the text data. In this case, one thing which might be a bit annoying is these are separated with spaces and not tabs. So if we want to change that, we can use sed again. So in this case, we're feeling brave. We want to use sed-i, and we're going to replace the space, in this case, with a tab. So obviously, you can't just put a tab in here. If you click tab on bash, it won't let you insert a tab. It will just do the annoying noise. But we can use this \t, which bash will interpret as a tab. So if we run this, and then look again in our file, you'll see these are now all tab separated rather than spaces. Okay. Now we're going to use awk, and awk can be used to, for example, extract columns. It can be used to do calculations between columns. A bit like grep, we can use it to extract certain rows if we want, based on some conditions. It's very, very powerful. In this first example, what we're going to do is just extract the first column. The first column in awk, or any column, is delimited by this $. If you have $0 here, that will return the whole, every column, essentially, so the whole data set. $1 should just return the first column, which in our case is just the individual number. So if we run this, you'll just see those numbers. Now we want some kind of conditional statement. So you'll notice if we cat our sample file, there's one fish that's from a different lake. It's from Lake Thun and not from Lake Zurich. We don't want that. We only want to look at these fish. So what we can do is we can use this conditional if. If in $3 we have Zurich, then print the whole row. And we can pipe this to a new file. So the larger than again here is using the piping. And we can run this. And what we have now is just the Zurich samples. These are in Zurich samples.txt, and now there's no Thun line. Perfect. You also see that we have a head length and body length. Now, what if we want standard length? We want the combined length of head and body. So awk can be used to do this kind of computation where we say add a new column, in this case column 6, because we have 1, 2, 3, 4, 5 columns. So we're adding a column 6, and we want it to do this computation, so 4 plus 5. So for every row, it will add these 2 and output the information to a new column. If we run this and check, here we created this new data frame just so we don't confuse ourselves. And you'll now see there's this final column, which wasn't there before. So this is the sum of these two. And then we can do a following kind of clarification line where we then say, well, we only want adult fish. And if the fish is below 140 millimeters, it's a juvenile. We don't want that. So we have another conditional based on this $6. And this time we're going to remove anything that's smaller than 140. So we're using actually larger than. We keep lines that are larger than or equal to 140. And again, we use print 0. And we're going to run that. And here you'll see, yeah, so we removed, I think it's 1 that had a small standard length. One of the things which you might do, which I don't actually have in this example, I might add it later, is you can obviously pipe these commands together. So if you're familiar with the pipe symbol, you can basically join 2 or 3 of these different commands using the pipe, which is this vertical bar thing. So you could actually do a lot of this in one go, just by piping together awk commands. And in that case, you wouldn't need to obviously give the input file. You would just say, do some filtering step, pipe, and then awk this, and then you could pipe that to a new file like this, or you could continue the chain of different commands. And you can also, because these are all used within Bash, you can combine any combination of sed and grep and awk and whatever you want to do lots of things. There's 2 cheat sheets here, I think, for awk. It can do so many crazy things you wouldn't believe. It can change things from upper and lowercase to each other. It's really, really useful for bioinformatics. It's very good at parsing the kind of language that we use. Are there any questions before I move on to writing scripts? Nope. Excellent. Okay. So, obviously, some of the things we do is this kind of exploratory data manipulation, as I've been doing this whole time. But for reproducibility and also to do bigger jobs, which we don't want to have to copy and paste or type everything every time, we want to be able to submit scripts. And Bash is great because it lets you submit things in the Bash language, which is very powerful, as we've shown. And to do this, what we'll be doing is there's a series here of scripts that we'll be making. I'll be making them all in Vim. Again, you're free to make them in whatever text editor you want. And this first one is going to be called firstscript.sh. So the .sh just means it's a shell script. So shell and bash, whatever. It's all the same thing. We are going to make this with Vim, and we're going to copy this in. So this script starts with this line, this funny looking line, this hash, then exclamation mark /bin/sh. This is called a shebang. And depending on the language that you're coding in, this is telling the computer, I want you to know that in this case, I'm using the shell language, bash. And it gives some information about how to basically prepare the computer for what you're about to give it. If you were using Python, this shebang would look different. Perl, it would be different. This is going to be our very simple script. So all we're going to do is we're going to echo, so paste to standard output, the phrase, hello world. And then the script is going to exit. So you can exit the script. One thing which can also be useful is to make the script executable. So this means that you can, your computer knows that this is a script that it's allowed to execute. And for this, you can use chmod +x. Chmod is a whole thing in itself about changing the permissions of files and things like that. This command basically says this file that I've made is now, I'm telling you that it's an executable script. It gives the computer permission to execute it. That's good. I will fix that. So this should say chmod +x +x first script. Okay, you won't see anything when you click enter, but you will notice if you check before and after that the permissions here have probably changed. So this first row, when you do lslh, tells you permissions, write, rewrite, for example, and that file will now be an executable script. You can see this X at the end that these others don't have. And then we can just use // that's telling it a script is here. We can run the script. Again, I've got the wrong script name. And you can see that after running this script, it will paste hello world. Perfect. So now we're going to make a bit of a more complicated script. This is more akin to something you might actually want to use for something rather than just amusing yourself with posting random things. We're going to make a script called countlines.sh. And we put this in here. And so this is combining the information that we've learned before about for loops for the files that we just made in this directory. So it's going to say for every file in the current directory that starts with oh no _file. And here we use this wildcard. So the asterisk is going to be used a lot, probably in your day-to-day work. And this means anything. So the file has to start with this, and then it can say anything. This could say, oh no, file, blah, 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 .faster.txt, whatever. In our case, we know we have oh no file 1 through 6. do. And then what it's going to do is echo the name of our file in this case, because that's what we're telling it to go through. And here we give it another command. So it's going to say the line count is, and then we do wc-l, which calculates the line count, and then our file. And then done means we're finished with the loop. So we need to chmod, and then we can run the script. And you'll see that it says the line count is 4, and then it says the file name. This is just the output of wc-l. And we have file 6 here, which of course we produce by catting the other two together, so that has double the number of lines. So that's great. So if you get sequencing data, you often do something like this to figure out how many lines you have or how many reads you have. That is the first part of the bash refresher.